Well, we have another example of breaking off. And this time, I just change the situations. Earlier, I applied a force from above. Now, I am giving you the length I compressed initially. Now, let's read the statement of the problem. Two bars of same mass. That means its mass both will have the same mass. मैंने फिगर ड्रॉ करने के मुसीबत से बचने के लिए एम उसी फिगर को रहने दिया, but they got same mass. Two bars of the same mass m are connected by a spring with a spring constant k, right, and a negligible mass. Okay, spring का mass negligible है, we all know it. हम हुक्स लॉ वाला spring यूज कर रहे हैं. The spring which is in an undeformed state is compressed by a certain amount delta L. मैंने ऑलरेडी कंप्रेस कर दिया है इस स्प्रिंग को डेल्टा एल से. Bringing the bars closer together. In this position, the system is placed on a horizontal table so that the spring axis is vertical, as you can see here. Find delta L. If after releasing the spring, the system jumps off from the table, तो वो jumps off just contact break होता है. So we all know that the spring should apply a force greater than equal to mg. That means in the limiting condition, if the lower block separates from the table, then the spring should apply a force on the lower block that must be greater than equal to mg or equal to mg in case of the limiting case, just breaking off. And the kinetic energy of the blocks at the moment of separation must be zero, as I considered in the last example also. So we can equate the potential energy of the system in the initial and final states. So I'm going to take, for gravitational potential energy, I am going to put datum here so that gravitational potential energy is zero here. And I'm going to start writing the equations. Initially, the energy loaded in the spring was simply k delta L. It is already given. So k delta L square upon 2 plus ऊपर वाले ब्लॉक का नीचे वाले ब्लॉक का तो ग्रेविटेशनल पोटेंशियल एनर्जी हमें लिखना नहीं इनिशियल स्टेट में, ऊपर वाले का लिखना है. दैट इज व्हाट, तो एम जी. And I need to consider the natural length of the spring, that is the undeformed length of a spring. I just took it in the previous example as L. So and it is compressed length delta L. So now the length of the spring must be L minus delta L, so that its potential energy becomes mgl minus delta L. That is the initial potential energy. And final potential energy, I don't know. A spring must have been stretched some length, and extension in the length of a spring, I suppose, is equal to x, so that I can write the potential energy loaded in the spring as half kx square. And m2, that means m2 must be at the length L plus x. Natural length of the spring, I supposed, is equal to L, and it has extended a length x, gone further a length x, so a spring is extended by a length x. So the gravitational potential energy I can write for the upper block, lower block is here only, so this will be equal to mgl plus x. That's right. And after what, after writing this x is I can find writing equilibrium condition for m1 when it just separates from the table, that mg equals kx. So I got the value of x equals mg by k. And now we can write the equation and that will come a quadratic. I needed to find out the value of delta L. So after putting the value of x, I will get some equation like this: k delta L square by 2 minus mg delta L minus 3 by 2 m square g square by k equal to 0. This is a quadratic equation in delta L, and after solving we get a positive value of delta L, that is equal to 3 mg by k, and that's it. That is going to be your answer. So because only positive root has a physical meaning, the negative thing is delta L is the length we compress, so it must be positive. So I taken the positive value from this quadratic equation and I got the value delta L equals 3 mg by k, and that is the answer. Thank you very much for watching this video.